Hello, Namaste. Myself Rohini Mergu from Walchand Institute of Technology, Solapur, talking about antenna radiation measurement. At the end of the video, you will be able to find out the shape of the radiation pattern of the antenna under the test. So, as I'm talking about the radiation pattern, let us define the radiation pattern. Radiation pattern is nothing but the energy radiated by an antenna, which is represented by as a radiation pattern of the antenna. Radiation patterns are diagrammatical representation of distribution of radiated energy into space as a function of direction. These are the radiation patterns which are shown here. This is called as a radiation pattern, and here this is called as a main lobe. Those are called as a side lobes, and the back side of the main lobe is called as the back lobe. This is also a radiation pattern shown, and this is a 3D visualization of a radiation pattern which is unidirectional, where the main lobe is much larger and the back lobe is much smaller. We need two antennas for measurement of radiation pattern. One will transmit, other will receive, and one is origin, other at the same distance away from the first antenna. There are the two procedures for measurement of radiation pattern. The first procedure is suitable for low frequency antenna measurements, and second procedure is suitable for high frequency antennas. Let us see at the first procedure, which is used for low frequency antennas. Here, primary antenna is not moving. Usually, we use the primary antenna as the transmitting antenna, and secondary antenna is moving in a circular path at a constant rate. Antenna. The field strength readings and the direction of the secondary antenna with respect to primary antenna are recorded along the circle at different points. And the plot of the radiation pattern made either polar form or in the rectangular form. So we can plot in both ways, either polar or rectangular form. So this is the setup for measuring the radiation pattern. As we say, the primary antenna is fixed, which is not moving. The secondary antenna is rotated along the primary antenna in a circular path, either in this way or this way. And we need to measure the output, or we need to measure the field strength, and we note the field strength, and this field strength we need to plot on either on the polar plot or on the rectangular plot. So once we measure the field strength of the by rotating this antenna at a constant radius, we can plot it like this. So this kind of a plot is called as a rectangular plot, whereas here when we plot it along the angles with respect to angle, then this is called as a polar plot. So this is what is the radiation pattern obtained of a particular antenna when we plot. The second procedure is which is used for high frequency antennas, where primary as well as secondary antennas are placed as fixed positions at a sufficient distance. Again, under the general conditions, primary antenna is considered as a transmitting, and the secondary is the antenna which is under test. Now the position of the two antennas are fixed, but the secondary antenna is rotated along the vertical axis. And we measure the field strength again with respect to the primary antenna, and the readings are taken at a number of points by stopping the rotation of the primary antenna for the recording and readings. Or we can take the continuous readings if the pattern recorder is available. If some computerized procedure is available, then we can take the continuous readings also. So this is the setup for radiation pattern measurement, where both the antennas are fixed at their positions, they are not moving, but the secondary antenna is rotated. This is the primary antenna, this is the secondary antenna. Secondary antenna is rotated around the axis, and the readings are noted, and these readings of the receiver are plotted either on the polar plot or on the rectangular plot. So as you can see here, again a much clear idea you can get. This distance r should be greater than 2d square by lambda, This distance r should be give the far field pattern, and this is the angle of rotation. Either you rotate the secondary antenna either along this axis or along this axis, theta or phi axis, and based on that you will get the pattern of theta or phi. But when we are doing this, the two major requirements are there: distance and the uniform illumination. So distances, you should get the far field pattern. So that there will be the accurate pattern measurement, and the wavefront will be illuminating the antenna under test very well. And this is possible when the distance between the primary and the secondary antenna is greater than 2d square by lambda. Another requirement is uniform illumination. That means the plane wave which is produced by the transmitting antenna must possess the uniform amplitude as well as phase over the complete distance of separation. So here the reflections from the ground, building, trees should be avoided. Means what? When I am taking the reading, there should not be any obstacles between the transmitting and receiving antenna and around the transmitting and receiving antenna. Thus, from the above discussion, we can say that pattern measurement of the antenna relies on the field strength of the antenna with respect to the direction. However, the distance and illumination requirements should be properly considered in order to get an accurate radiation pattern. These are the references used for preparing this video.